Good day, guys. Alright, so in this video, I'm going to give an introduction to alternating current in the matriculation physics syllabus. Alright, so we begin by asking ourselves, what do we mean by alternating current? Alternating current is a situation whereby in the circuit, the current, right, it reverses direction periodically. So it goes positive and negative all the time, and it changes its magnitude as well. And changes its magnitude with time. Okay, and let's illustrate that. All right, let's illustrate with this picture. On the left hand side we have direct current, and then on the right hand side we have alternating current. If you look at the brightness, so the brightness represents the magnitude. The brightness for the DC is steady, right? It stays the same. It doesn't get any brighter, it doesn't get any dimmer, unless we change the voltage, obviously. But the magnitude stays relatively the same. And then let's look at the charges, the movement of charges. It is moving in a anti-clockwise direction, right? And all of it is moving in the anti-clockwise direction. Let's look at the AC. It becomes bright and dim, bright and dim, bright and dim at the relatively same pace. And then, apart from that, if we look at the charges, the charge movement, it goes clockwise, anti-clockwise on at one point, and then it goes anti-clockwise at another point. So obviously we can't use the same notation or the same ideas that we use in DC and apply to AC. So what should we make? What changes should we make? Well, the first thing that you need to realize is that these changes, the directional change and the magnitude change, it changes with time. Okay, so it has to be a function of time of some sort. So changing or moving from DC to AC, you need to introduce voltage not just as voltage, but voltage as a function of time. Same case for current, where you have to say now that the current is a function of time. And this function of time, right, the relationship is a sine function. And the reason for that is because it shows periodicity. So it shows that it has period. If it has period, it has frequency. How frequent does it move from up and down or becomes more and less? Okay. Now, at this point, I would like to point out that your resistance, you did not make any changes to the resistance. Okay. Resistance, we have a special role for it later on. Okay. And the shape of the sine function, just to remind you that it looks like that. It looks like a wave. Okay. So next, there is an idea in alternating current where we talk about root mean square. Now you can find the derivation in my notes, okay, and many other physics textbooks. But let me present you with a graphical argument for it. Let's look at the definition of root mean square value. The root mean square value is a value for steady current, which when you apply it to a resistor, it produces the same power. So look at the word, the same power, as an average power produced by an alternating voltage across the same resistor. That means we have to look at power, not just voltage, but power specifically. That is our clue to figuring out how does our root mean square voltage relate to anything else. All right. So what do we do now? We make assumptions. We make assumptions and see if the power output is the same. So let's put our first assumption, which is, let's say the peak voltage for AC is the same as our voltage for RMS. So in this graph, you have your power output to be under the graph, right? So it's just the area under the graph. Is it the same? Really? To me, it's not. Why? Because you have these gaps here. See? These gaps here. Right? These gaps. So I can say that the area under the graph, right, under the AC graph, AC power graph, is not the same as the area under graph for the power time graph for DC, which is just a steady current, just a square, right? So now what do? Well, let's propose another idea and see if it solves the problem. That idea is that our peak voltage for AC is equals to the square root of 2 times the RMS voltage. Let's draw that out. Now, if the peak voltage for AC is equals to the square root of VRMS, is the power the same? It is. Now, it may not look obvious at first glance, but let me assure you that it is, right? So if you split this into half and you label it number 1, you can cut this piece off and then put it in here. Same case for a second piece, you can put it in here if only you split it into half, right? So if I can put it here, I can do the same for the second one, which is 3 and 4. I can put it in here, 3, and then here, 4. So at that point, we can see that, oh, right, the area is the same. So the power output must be the same, right? So now we have found a solution. We know, we have confirmed that it is a solution, right? So we can do the same, we can repeat the same argument for current, where we define the root mean square for current produces the same power. Again, the same word, the same power. Okay, so then what we have is the peak current, right, is equals to the square root of 2 times the root mean square current. Now we can just rearrange that and have an equation that describes our RMS voltage and current. All right. So in summary, when you go from AC to DC, from DC to AC, you have to change your voltage and current into functions of time. Number 2, you have to talk about the root mean square voltage and root mean square current, because those are going to help you with this idea of power. Okay, so that is all. I'll see you in the next video, alright?